All right, so now we're going to take a look at the issue of power as we go about designing an experiment. This is going to be really useful as we start our project because this is the first set of calculations or considerations we need to make, well, after we've considered which design to use and other bigger factors like that. Okay, so we've already defined the nature of type 1 versus type 2 errors. Remember, if we reject a null hypothesis when in fact it's true, that's a type 1 error. If we fail to reject a null hypothesis when in fact it's false, that's a type 2 error, nicely summarized in this table. So type 1 error rate, which Gary uses epsilon for, is easy to set. We just choose it. We often choose 5%, right? Because that's a well-accepted norm in research. Power is that probability of rejecting the null when in fact it is false. So we want our power to be high or low. Think a moment. High or low? We want it to be high because it's the probability of declaring a difference when the difference is actually there. Okay, so getting that, like Gary says, the lower right smiley face. We're happy there. We're happy there, but we're especially happy here, right? So power is a much more difficult to control value than epsilon. Epsilon we just choose and set. Power is a little tricky or tricksy. So we need to make sure we design our experiment in this class, but also any experiment you ever collaborate on to have the appropriate power. Now, what is appropriate power? That depends a lot on the discipline, to tell you the truth. For example, in the engineering disciplines, we assume very, very high levels of power. In social sciences, behavioral sciences experiments, we're measuring much more difficult to measure concepts, and so maybe we're okay with 70%. So, but in general, no matter the subject matter, when your power is low, you're wasting your time, honestly. You are wasting your time with the experiment because you don't have a high probability of finding what it is that you're looking for and finding those true effects. Okay, so an experiment with low power is worthless. But if it's too high, you might be wasting resources in your experiment. So you might be able to find something that's not, say, 99% power and spend your resources in some other way to make your experiment better. Usually power is between 0.7 and 0.95, like 0.7 being for, more behavioral sciences areas, and 0.95 I always think of the standard for engineering-based studies and other things with very precise measures. Okay, power for the F-test, and what we're talking about here is that global F-test that we use in that ANOVA, okay, that we've been looking at a lot. So that F-test for comparing your separate means model with the single mean model depends on practically everything. I tripped over that, sorry, Gary. It depends on your type 1 error, which we set, okay? But it also depends on your numerator and denominator degrees of freedom. What is G? What is N? What is G minus 1? What is N minus G? Okay, and what effect does that have on your distribution for the F, okay? And then there's also this thing you may remember from your math stat class, hopefully you do, especially if you're taking it, right? That non-centrality parameter for that F distribution. If you don't remember what this looks like, go open up your math stat book after class and take a look at this, okay? This non-centrality parameter, the null distribution of F, by the way, has a non-centrality parameter of 0. Okay, but when it's non-zero, it depends on those sample sizes, the N1 up to the NG. So those number of replications per level of our factor in our model, and the non-null treatment means, so those ones that differ from the grand mean, as well as the error variance. So here we have, 1, 2, the numerator denominator degree of freedom, and this non-centrality parameter, which depends on a host of different things. So it's complicated, okay? Under the null, the F statistic follows a central, hence that non-centrality parameter is 0, with G minus 1 and N minus G degrees of freedom. Combine this with epsilon and we get a critical value. Reject F for any value larger than that critical value. And we've done this, we tend to use the p-value in class, of course. When the null is false, however, this is where we are thinking when we're thinking about statistical power, because if the null is false, then we should be able to detect deviations from that null, right? And that is what power means to us, the probability of correctly identifying those deviations from the null model. Okay, so under the assumption that the null is false, that F statistic will follow a non-central distribution with the same degrees of freedom. That distribution is going to be shifted to the right, away from 0. And that non-centrality parameter here controls the amount of shift to the right. And the probability of being to the right of the critical value is going to be that power, because that critical value, if we're above that critical value, that's the cases where we're detecting deviations from the null. So being to the right or greater than that critical value under an alternate distribution is going to give us that power, that area under the curve to the right, I should say. Example, okay? So we might have a null distribution here for the F distribution. Under the assumption of the null hypothesis, the F distribution would be this paler, thinner line here. And then our area to the right, this would be our critical F value right here, and our area to the right is just, that area is epsilon, okay? However, if we deviate from the null hypothesis, we have a non-centrality parameter for the F that shifts it away from 0. Okay, so we get something where the area to the right is going to be bigger, and hopefully we want this to be really big. Okay, you can see the more we deviate away from the null distribution, the bigger this area to the right is going to be. So if we have means that really vary wildly from the grand mean, then we're going to see something where that area gets pulled over and over here. So this area to the right is going to be quite large if we have deviations that are quite large. As you decrease epsilon, it becomes more and more difficult to reject that null. So that moves that critical value to the right. So you need a bigger and bigger F statistic in order to reject. So if G is fixed, if N is fixed, and if your non-centrality is fixed, then a smaller epsilon leads to lower power because it gets harder and harder to reject. Imagine just again, if we go back to this, if we're moving this further and further out, the area of both the null distribution and the alternative F distribution is just going to get smaller as we move this line further out. Epsilon is a measure of how far the alternative state of nature is from the null. So the more shifted to the right it gets, the further away we are from the assumption of the null hypothesis. Okay, so we replace the data with their respective means and then fit the null model to this data. General rules of thumb about this non-centrality parameter, it's going to increase if you increase your sample size. Again, that makes should make intuitive sense, right? Because as we collect more data, we get more and more information to help us make a decision between the null and some alternative. Epsilon increases if the error variance is smaller. That again should be intuitive. If the random error in the model is small, then it'll be easier to distinguish between the null and deviations from the null. It'll also increase if the means are further apart. So if there's more deviations among the means and from hence the grand mean, that non-centrality parameter will also increase. This is the one I intuitively always think of because that's really what we're interested in, right? These other things also affect it though. Sample size being an important consideration like we've talked a lot about in this class. Okay, so here's a formula, computational formula. Remember the effect notation we use for the means. So those alpha i's are our effects. Remember that they sum to 0 by assumption for our CRD. So if we sum up those squared effects and divide by our variance, our error variance, This gives us that non-centrality parameter. Note that the expected value of the mean square for treatment is going to be something that resembles this quite a lot. It's the error variance plus this quantity here to the right. So if we know that our mean squared error is sigma squared, which is our assumption, we can start to see how there's some similarity, and we can use this information of the MS treatment and MSE to help us know something about the non-centrality parameter. A discerning student, as Gary likes to say, will remark that this non-centrality parameter depends on a lot of stuff we don't actually know. Like, we don't know the mu i's. We don't know sigma squared. If we knew the mu i's, we wouldn't be doing the experiment in the first place. So how in the world can we go about estimating something that depends on something we don't even know? Okay? In general, and I like that Gary points this out because it's a reality check. Power analysis and sample size selection is a big exercise in let's pretend or let's imagine or what if, okay? So when I do a power analysis for a client, let's see, I have an appointment to do this later today. I'm saying, let's just pretend that your experiment goes perfectly and that we know exactly what the error variance is going to be, and we can kind of discern what kinds of effects we're going to get in the experiment. And I'm going to base your sample size estimate and power, estimated power, upon those assumed characteristics. Okay? It doesn't mean it's really going to hold, but it's our best guess. It's our what if or let's pretend. Okay, so we can control epsilon though. We can also control the number of replications. So those are two things that we do have full control over to some extent. I'd say maybe not the number of replications because sometimes you run out of time or money, right? But epsilon certainly. Otherwise, we're plugging in some hypothetical values for the means and the error variance, and we're doing our best guess. These values should also correspond to what we know about the subject. So when I talk to a subject matter expert, I ask them, what do past studies say about these means? What do you know about it? How would you describe it? And we kind of get at what we know from the body of research in that field. Thus, to make power analysis useful, we need to specify some practically significant set of alternative means. That's why I usually start by asking the scientists, what do you know about this phenomenon? What is your guess about what the means should do based upon what is understood? And then we also need to guess how large the variance is, also based upon vast research if we can. Some people like to think of those treatment effects as being multipliers or multiples of sigma. And while that's mathematically true, Gary doesn't really like that. He thinks it's a bit of a cop-out when you're specifying alternatives. So this is a opinion, we'll just say that. I think there's some cases where I would use that and others where I just run it. I would always lean on the investigator more heavily for this part. Find your alternative means where you say, if this were true, I'd want to know about it. So that's what I usually start out with consultees, is I say, what kinds of practical effects are you really interested in knowing about? And we kind of base those hypothetical means upon that, because those are the things we really do want to be able to detect with power. Makes sense, right? All right, I'm going to stop there and we'll continue with another set.